Okay, so now I want to look at problem 35 from chapter 23. Okay. Here we have a flat ring of inner radius R1 and outer radius R2 that carries a uniform surface charge density sigma, and we are to determine the electric potential at points along the axis. So we have thick ring. So this is the axis they're talking about, the symmetry axis, which they call the x-axis. The inner radius is R1, the outer radius is R2, and we have some uniform charge density sigma on the surface. Okay? So this is, if you look at this from face, it would look perfectly circular. I'm trying to reproduce the figure in the book. The figure in the book is much better, obviously. And they're telling you try substituting variables. What variables? Anyhow, we'll see. I don't understand the hint, but we don't actually need the hint. So this is actually very similar to one of the examples in the book. So in that example, this was completely full, but we can proceed in exactly the same way. Okay? So in that example, you were just dividing this ring into concentric, circular, very thin rings, and you will integrate the radii of those rings from 0 to the outer radius of your disk. Now, you don't integrate from 0 to the outer radius, but from some inner radius to the outer radius. Otherwise, the procedure is going to be exactly the same. Okay? So let us throw some very thin circular rings here. Okay? Just something like that. So these are going to have radii r and of thickness dr. Okay. And by integrating over this, by calculating the potential due to these rings and adding them all up, I can calculate the total potential, right? So my potential at some point, let's say some point x, is going to be just the integrals of the potentials coming from these rings. And each ring has this nice property that from this point, P, that I'm looking at, all the points on the ring are equidistant. Okay? Now remember, this actually looks this way. So if you're coming from the symmetry axis and you're just looking at one of the rings, all the points on that ring is going to be equidistant from the point, from any point on the symmetry axis, okay? By symmetry. So I don't need to calculate this for everything. I just need to calculate it for one of the points, and I can just integrate trivially over the ring. Okay? So I can just basically assume that all the charge on this ring is concentrated at a single point of some distance that I'm going to figure out. Let's call this distance d. And let's say that this ring at this point has radius r. So this is also r, that d is going to be x squared plus r squared to a half. Okay? And that dv, and consequently, is going to be some dq divided by 4 pi epsilon naught d, where a d is given by this expression. Okay? We are looking at potential, so it's not d squared, but just d. Now what about dq? Well, dq is the charge on this ring, and that charge is going to be the area of the ring times this surface charge density. So dq is going to be the surface area times sigma, and or let's call this sigma times ds, because it's an infinitesimal area. And well, how do I find that infinitesimal area? Well, this is like a strip, and I can just open this up. Because it's of infinitesimal thickness, I can open this up. If it was finite thickness, like the whole ring here, I won't be able to do that without tearing it up. But for infinitesimal ring, I can actually open this up, and the surface area is just going to be height times the length. And the length in this case is just the circumference. For this ring, the circumference is 2 pi r, and the height is just dr. So this is sigma 2 pi r times dr. Okay? So let's write this down, RV. Now, to cover the whole ring, my r has to go from r1 to r2. R equals capital R1 to capital R2. Sigma 2 pi r dr by 4 pi epsilon naught times d x squared plus r squared to a half. Okay? And this integral can be done, and that's probably what they mean by substitution of variables. So the easiest way to take integrals like this is to make a substitution of variables. You call r squared u, then 2r, the r is going to be du. Okay, so this is going to be du, and this is just going to be u. So, excuse me, then the integral becomes simpler. The integral of this is simply this x squared plus u to 3/2 power in the denominator, okay? And some constants, but you can take the integral. I'm sure this must have already been done in the example, so I'm not going to go over this again. And probably that's what they meant by substitution of variables, that try substituting variables. I don't see anything else that's useful here. So the key point here, as also for the example in the book, is that recognizing that because all of these points on the ring that you're choosing, so you're integrating over this ring by dividing it into infinitesimal thin rings, and all the points on those rings, for a given ring, all the points are equidistant from the point on the axis, and because of that, I don't care where they are. Okay? I can just say all the charge on the ring is at some distance, x squared plus r squared square root. Okay? And I can do this because the potential is scalar. You can't do this for the electric field. It just doesn't work because they are going to produce different electric fields. What you need to do is to recognize that by symmetry, their off-axis components are going to cancel, and you will need to calculate the component that's parallel to the axis, and then you can say, okay, all of these contribute the same. Because they are same distance, they make the same angle, their x component is going to be the same. Okay, but you can't just add the magnitude of the electric fields up. Okay, because they are vectors, you have to do a vector addition. But for potential, you can, because it's scalar. If all the contributions are the same, if they're all little charges of the same magnitude at equidistant, they might as well all concentrate at a single point. And this is something that you can apply to problems with high degree of symmetry.